So I am going to sketch out something like a framework for the physics of agency. Some of this will feel very familiar or obvious. Hopefully some of it feels contentious or somehow exciting. And this is kind of a bold claim from quantum foundations to cognitive implications. In my recent work, where I've been doing a lot of work at Simplex, where we've been thinking about representations that emerge in neural networks, as you do the standard training them to predict the next token. There seems to be like this platonic form of representation that they have, which is one of the major questions for me right now, which I think fits naturally in terms of agency. To what extent do intelligent agents represent the world in the same way, and to what extent do they represent it differently? How will that affect our interactions? So my talk will be skewed a little bit in that direction, but I think also part of this is initially we found this thing of, oh, these neural networks are representing something like Bayesian belief updating. We find these pretty fractals in residual streaming transformers. But then it also turns out that if you train networks on certain types of data, it's just classical tokens, but sometimes there'd be a more efficient representation if you had like a quantum world model and then you do Bayesian updating over that. That happens in these neural networks. So then it's a bit like, well, what is quantum really, and what is classical? And there's a natural part of the story which is even like post-quantum, and it's just these kind of natural ways to represent things in when your memories are allowed to be stored in a real vector space, which I would argue basically happens. Like, I think most examples we have of intelligent agents, humans, and to the extent that you grant to other animals and AI systems, they're effectively working in a real vector space. And so that's kind of what I'll propose is, if we take some of that stuff seriously, we can learn a lot from just saying, what are the implications of this? So it's going to be a sketchy framework, 2 results, and a lot of questions. And feel free to interrupt and heckle. So here's a few bold claims. I suggest that within 5 years, we're going to understand intelligence basically like we understand physics. Like, this is the rules, this is how it works. There's plenty of instantiations of it, the same way you know many physical systems. But I claim that we're going to understand this stuff. So if that's true, exciting times. But we've got a long ways to go. I'd also claim that we're presently pre-paradigmatic, and hopefully some of what we can do here is figure out, both for intelligence and agency, what is the framing we should have? What are those questions we should have? And in terms of understanding intelligence and agency, I feel a lot of urgency, mostly from an AI safety perspective. I feel like it's crucially important to figure out what's going on, what are the implications of bringing these AI systems into the world, and then, whether or not that goes well, it is a new opportunity to understand ourselves and hopefully have better interactions with each other. So that's pretty nice. And with the new AI systems, we can test ideas quickly. So we're not stuck philosophizing. We can actually do something about it. So here's some observations. They're pretty simple, I think. Agents are physical, and the world has many parts. What happens if we take this seriously? So let's start. Agents are physical. So memory is physically embedded, and as I've already said, memory can be embedded in a real vector space, and that's important, and it's different how we often think about it when we design memory elements of a computer that are in these metastable wells, and they're mutually exclusive, and we think of information theory as what happens with these discrete elements. So there's something maybe new that can happen here. Agents also, yeah?
Sorry, just what do you mean by real vector space as opposed to vector space?
I just mean a vector space over the real numbers. So typically we think of like real or complex vector spaces, but you could also have other more exotic fields. But basically, the familiar type of like generalizations of Euclidean space, basically. And so
the
you can think
distinction you're drawing is between the conventional discrete picture
that's
of information.
that is mostly
the continuous spaces.
that's right. So I'm mostly talking about continuous space, and you can think of even like brain activity. Maybe there's some basis set of functions, and that's like maybe a basis for the real vector space. For neural networks, neural activations live in some like you can describe it by a high-dimensional vector. Yeah.
Yeah, I was gonna say for the brain stuff, like maybe synaptic weights are the better understanding of memory anyway, because if you wanted to take a dead animal and take its memories, you would take the synaptic weights. You don't have activity reference.
Yeah, and that's I think an interesting question of how much can you revive of an animal by taking its weights. There will be something about it, but also something seems dead and gone permanently when its
Yeah.
neural activity is not going. But you guys would know this better than me. But
It's a good question.
I mean, is it like waking up? If you just you take the weights, you kind of reinstantiate it. Is it like waking up, or is it more abrupt than that?
Isn't this a dream of Silicon Valley that they can like basically upload their weights to some computer and like
Sure.
somebody
Yeah.
can download their weights
For a
later?
while.
Yeah. Well,
That
even
doesn't
more
mean
reason
it's
why
well motivated.
important to understand, right? Yeah, if we're like, when we're uploading ourselves, what's that going to be like? And I'd also argue that that's not us, even though it had shared history, so all sorts of things.
But I think the brain can be totally inactive, and then it can function. Person will have the same memories and kind of personality. Yeah.
Same
Things are-
long-term memories, yeah.
So
Yeah, right. Yeah.
it seems like there's a motivation behind this framework, which is that functionally AI and machine learning operates in real vector spaces, perhaps because floating point operations are easily implemented in modern digital circuitry. It seems like we could talk about complex vector spaces or Hilbert spaces if we assumed that our machinery was quantum mechanical.
Yeah, I don't think it makes a big difference. To be honest, like you can just basically, if you have a complex vector space, you have your real vector space, and it's kind of the same, I would argue. But there are some advantages, like I think Chris Hiller has a paper where he's trying to really make some networks complex, and you get some interesting representational stuff there.
I suppose my point is that the hardware that you're familiar with perhaps affects how you might choose to embed memory.
Yeah, and I think maybe the reason that it was chosen was for something else, like it's easy to do matrix multiplications, and then it turns out, like, why is this thing working well? And maybe it turns out because that availed to certain representations. That's a bit of what I'll argue. Okay, and then the world has many parts. This feels like maybe a different part of the story. But there's something like quite deep that I'm coming to realize, that agents will represent and act on multi-part type systems, and that has very important implications for basically how many dimensions we need to represent the world. Why don't we represent things all at once? There's some ideas from complexity science and even more like Eastern thought that maybe we should focus more on holism and just represent everything all together. But there's actually a huge dimensional advantage by recognizing objects in the world and recognizing other agents. So I'll hopefully be able to at least gesture at that and how that plays out. So part of what we're finding, I'll argue, is like why agents identify objects at all. So here's something like the two answers and lots of questions that I said. So that memory can be embedded in a continuous space. It means that you have these not only quantum and post-quantum dimensional advantages for representations. Not only quantum, because over the last decade or so, quantum foundation people have discovered these and said, hey, look, if you use quantum memory, you can do things with fewer dimensions. But it was really just something about being in a real vector space. So I'll talk about that. And the world has many parts. I already gestured at exponentially fewer dimensions if you represent objects. So let's see if we can get to that. The world has many parts. This is more words than is needed, but basically you can represent, so this is kind of core physics stuff, you can represent the state of the world in some large Hilbert space H, but there, is often a natural tensor product decomposition of Hilbert space. Let's say there's big N parts, and then you can say, oh, my Hilbert space is just the tensor product of those things. Well, which tensor product should we use? There's actually this quite nice paper by Zmerny, Leiter, and Lloyd, where they suggest that even when you think about canonical entanglement of a Bell pair, that's already assuming a particular tensor product decomposition in Hilbert space, and has to do with what we think we normally have access to. In fact, there's a different representation of the space. So if you're familiar with the fully maximized Bell states, there's 4 of them. Usually goes by the name of like psi plus, psi minus, phi plus, phi minus. Kind of a silly thing, but they talk about it in this paper, and it's cute. Okay, well, we're going to change the tensor product representation to be something like psi phi plus and minus, and now what's an entangled Bell pair in that case is just a product state. So wait, what do we mean by entanglement, and which things are the parts in the world has to do with how we, as agents, think we can interact with the world. Right? So I think that's maybe just an important reminder for physicists that the way that we decompose the world is a choice and often has to do with how we interact with the world. Okay, so here we are, walking through the world, looking at it with maybe our more sophisticated instruments than this. Here's a bit of my mind, what came to mind when I wanted to represent an environment: palm tree, rock, bird, and some other agents. Okay, so we can at least chunk the world into the agent and the environment.
Wait, so are you implying the bird's not an agent?
I don't
You should
wish
just-
to make a claim one way or the other. Of course, the environment can be further decomposed into parts. Some object, some other agent, and so on. Well, and then also, if this is really an intelligent agent, the way we are, it probably has some representation of the environment and even of itself. Well, this seems a bit paradoxical, right? Like, how could all of this be contained within itself? So that can't be exactly true. But there's some maybe lossy version of that. So the space of the agent probably contains some part of its space is allowing for a representation of itself and everything else. And there's some interesting thing in the framing here for us to think about of when we're talking about belief updates over the world, to what extent are we talking about of the world, and to what extent are we talking about of the model's agent of the world? There's often a lot of nuance there.
Yeah, we're going to use this to argue for your decomposition.
What's that?
The point you're making here, you can use it to argue for the decomposition, conditional independence, breaking things into subspaces,
Yeah.
and so on.
Yeah.
You're motivated by the limitations of the agent.
Yeah, exactly. Yeah, to the extent that this decomposition is a choice, it doesn't make sense to attribute it to the environment by itself unless there's an agent acting in it, actually. So I think that's a good point. Okay. And it feels useful to me to just point out the different ways that the quantum state of the environment can be. In general, we could have some probabilistic combination of pure states, but it's over this multipartite environment. So generally, you would be entangled there. If the state of the environment was separable, so then it's kind of described by how it is everywhere locally. Okay, then it would be non-entangled. And then there's this even further specialization that if you had this product state, typically what I hear physicists say, and I recognize I used to say, is that this indicates a totally uncorrelated parts. You can just describe how the world is everywhere, and it's totally uncorrelated. There's literally a quantifier called total correlation, and it's 0 if the world is like that. One of the things I'm coming to realize is that's a pretty bad description of it.
It's terrible.
What actually is happening is, as you've operated, you've operated in the world, you've observed in the world, and if this is the state induced for the agent, this implies that all of those previous operations have induced conditional independence given that history. But kind of by themselves, those parts can certainly be correlated. So there's a lot of nuance here that I'm coming to realize as quite important. And
How can they be correlated if they're conditionally independent?
they are correlated if you don't take into account the variable that makes them conditionally independent. So in particular, I can say there's some, let's say I'm doing like a belief updating, which is effectively how you get density matrices. You can have these parts of the world are conditionally independent given the set of observations that have led up to that. However, if you were not conditioning on those observations, you would just say, hey, these things have something similar going on, and they'd be correlated.
So you're saying it's possible to induce correlations by observing more. Is that you're basically saying that it's like an XOR gate. You look at the two random bits and you're like, these are uncorrelated, but then you look at a third element and you're like, oh, actually there's correlation between them. So you're allowing for the possibility of induced correlations.
Yeah, and in I think language you would be familiar with, if we say that we're going to have belief updating by some linear operators, which is like from parts 1 to big N by some transition matrix of like, let's say x of n given x up to n, and you update according to this thing. Sorry, not everyone will be able to follow this at the moment, but if you condition on the history, the parts will be conditionally independent, and you'll have, let's say, simplices in parallel that there's correlation, but you can think of the Bayes net, that the Bayes net renders them conditionally independent, right? But if you totally marginalize over part of the Bayes net, then they would look correlated.
Base nets allow you to represent cycles.
That's correct. They're
I
decks.
think that's a misrepresentation of causality in the world. And in a particular time, they can't represent time. So
Bayes nets are a way of representing conditional dependencies.
yeah, and that can seem to be agent. The word can seem uncorrelated because of that. That's missing structure.
Yeah. So something about this actually is going to allow a dimensional advantage that you don't even get in this case, and that's maybe for now a claim and for a conversation later. Okay, so usually in agents, or at least for RL, reinforcement learning setup, you think about actions and observations, and there's time indexing and all this, and it's like, well, for us, where do the actions happen? Where do the observation happen? Where do you draw the line? How do you demarcate things? It's a little unclear. Anyway, something happens, and the world updates, and the agent updates. So however you kind of partition this thing, so you could say, okay, well, there's something like the action alphabet and the observation alphabet. But anyway, there's this joint thing when you condition on the state of the agent, the world, everything changes. And interesting when I'm saying conditioning on the state of the agent, that means that the representation, the new density matrix, if you will, it's relative. It's relative to the observer, right? So that seems important and relevant, that we could be carrying around different descriptions of the world that I could even imagine they're incompatible, even though they're both justified. So this is an interesting thing to come.
Well, also, if you have an agent that's with the name, they may take actions, make decisions that affect the world, that change the world, and therefore they need to update again, perhaps a whole new inference cycle.
Right.
So there's the point I just made about time is just built into this at a very deep level when you talk about updating. writing down the full dynamics.
Yeah, there's an incredible amount of richness that I'm bearing into effectively in this notation a super operator induced by y, something about the agent on the density matrix, the former state of the world, and then you just basically have to renormalize. That's what's going on in the denominator. Okay, and then maybe this is just, I don't have much to say about this, but maybe we want to say something about rewards in the world, I'm not sure. But to the extent that rewards are a function of the state of the world, and the state of the world is basically hidden to us, well, the agent probably should, in some sense, have something like a world model and do belief updates over that as it acts and takes observations. That would allow it to maximize reward if it, at least to experiment with some things and understand, build a model of the world and reward. And the value of actions as a function of belief state, maybe the value of the action depends on the state of the actual world, but you only have access to that in relation to what you think that state of the world is. So anyway, there's a lot to go into, and this isn't my expertise, so I'll defer to later discussion.
That's where the reinforcement learning comes in. That's their paradigm.
That would be basically their paradigm, yeah.
We propagate the stuff back in time for reward.
Yeah, so I'm curious if you guys have hot takes on this. I'd be excited to hear that over the week. Okay, so, well, for me to be able to say maybe something useful to you in the next 5 minutes, I'm going to just assume for now that agents track beliefs over a world model. These beliefs are stored as vectors in some space. And the beliefs are updated. Bayesian updated as actions and observations go. For some of you, this might look familiar. Basically, we can say, what's the probability of some sequence of observations given some sequence of actions? And I'm going to assert that, well, because this is the way physics works, there does exist a linear map for calculating these probabilities. So if there's some initial vector, let's call it a predictive vector, initial predictive vector, there is a linear map, and then this thing you can think of as just like the trace operator that exists. This guy's just a composition of linear operators. Then, if we want to know the probability of future observations given future actions and also past actions and observations, then just according to this thing, this is just Bayes' rule, basically the probability in the numerator here, the stretched numerator, probability of the joint divided by probability of the marginal of the past. What this says is whenever a past action observation pair induces the same vector here, it cannot affect the future differently. This is reminiscent of predictive states, causal shielding, causal states, I think, Alec, your recent paper talks a bit about this sort of stuff, and one of the things here is this gives this geometric picture of this, that whenever an action observation pair induces some vector, it can affect the future differently, and these vectors, these histories have some embedding in relation to each other, so there's some geometric aspect of that. So some geometric aspect of that, there's some updating from how you go from this A to W, some induced past, to some, you tack on a new action observation. So there's kind of a mechanics to do here, which is probably familiar. And maybe something useful I can point out, that different assumptions about what memory is like implies different dimensions required to do this stuff. If you thought something like there's a hidden Markov model that describes the world, you'd have these discrete latent states and you try to do belief updating over that, your beliefs would be in a simplex. We know from quantum mechanics that you can have kind of this continuity of of pure states that you can have absolute certainty in one thing or the other, and those things can be non-orthogonal. And that's very important. You know, it could be 0 or 1, or 0 plus 1, or 0 minus 1. Those are all different, right? Everything in between. And you have uncertainty in there. What we found when we train neural networks, as I said, is when it's advantageous to represent a quantum world model, it'll do it. And so it can use, say, like 2 dimensions instead of infinitely many that would be required for the minimal HMM generator. And there's even these post-quantum things, which is really just to say, let's just zoom out a bit. You know, even the physics framing's not, it's like too strict. Really, what agents want to do, I'll claim, is take advantage of linear maps updating the world, and the analog of Bayesian updating via linear maps is this very general thing which allows for dimension reduction. I don't have a lot of time, so I think I'm going to just kind of say we find pretty pictures of representations in neural networks. You can think about this as updating density matrices, or similarly, there's a representation in terms of generalized block representations. This stuff emerges over training. And there's that universality I mentioned at the beginning, that whatever the architecture is, at least for the neural network, if it's transformer or LSTM, the thing just wants to learn this universal representation, that you look inside the neural activations and we can anticipate. There's like some ground truth structure of how you want to represent the world, and then we find that linearly represented in these different architectures. And again, when it's more efficient to represent the world with something like a quantum world model, then it does that. Okay. Very briefly, this is getting to back to the conditional independence and the world having many parts. So you have this belief, A to W, basically this history W induces this belief. When it has this tensor product decomposition, and when the update on the agent state maintains that tensor product decomposition, then okay, that's great. Then you can track the world by tracking this thing. But you think, what's the dimension of this? Well, if each part has some dimension Sn, then it's the product of all the Sns gets you into this space. But all of the information is just in each of these guys. So I should just be able to talk about how this eta 1 is, how eta 2 is, and so then it should be like the size of S1 plus the size of S2, so linearly rather than exponentially. So in fact, forget the words. This is just that when you have this tensor product, the product state structure that's preserved in your beliefs, we anticipate that a good agent that's efficiently using its representation space will just represent the direct sum, effectively, of those beliefs. And we can test this by saying, okay, the observations in the world have this decomposition, even in the case when these things are totally independent, but you don't get to observe the parts independently. You just get a big observation of the world. Does an agent learn to chunk things into parts? Okay, so then the probability over the next latent, over the next belief, given some history, it should factor, in principle. You'd go from that product space to the sum of spaces. And when we train neural networks on this, we find that basically the neural network does find a representation. Here, the parts were basically, if you're familiar with Sarah and others' work on this, there's 3 MES3s and 2 of these quantum processes that the network would have to discover. And it does discover it. It learns how to factor its tokens, and it learns how to factor its representations to basically, this is showing how many dimensions does the model take up over the course of training, and it goes from many, many to small, and then it learns, aha, I need 10 dimensions. Whereas if you represented everything in this holistic space, you would require here 3 cubed times 4 minus 1. I don't know, a lot.
Do you have like an order of magnitude for 3 cubed times
27.
27
times 4?
27
So,
times
so
4
like
minus
100. Yeah.
Yeah, so like
Yeah.
you, instead of needing like on the order of 100 things, it's exactly learning, there's a refactoring of my representation space where I recognize parts in the world, and that is what neural networks are learning. Even just, we're not telling them to do this. This is just standard like next token prediction, and I'd argue that most of us agents are motivated to predict the world in service of all this other stuff, like I was saying, maybe rewards and all this. So my guess is that most of us agents will find these decompositions of the world into parts in other agents, sometimes classical, sometimes quantum. So hopefully this is a useful contribution to you.
I'm not sure they want to.
No, yeah,
I think
it's the wrong word.
Motivated to.
No, I think no. It's a property of statistics. If you can do your inference in a lower dimensional space, of course you're going to do that because it's going to be exponentially less samples you need, and the compute's going to run faster.
Yeah.
Doesn't have to be a desire. It's just going to build in.
Yeah.
Because you're comparing inference across different dimensional spaces. As soon as you factor that, you reduce the effective dimension. I just reframed
Yeah.
what you
I agree. Want's a strange word to use. I don't think we have choice over the matter.
Well, this is the meeting on agency. So what exactly constitutes a want? Maybe a pressure for simplicity.
I think if anything, we sometimes might need to want to represent things in a higher dimensional space to say, I don't want to have this oversimplified view of the world. I want to consider the implications of my actions. And then you are forcing this joint space, and it's really hard to think about.
Right.
What are the implications of my actions in the world? We might need to want that if we're going to do something about that. Maybe the natural thing.
Or want to need it. Or want to want.
Yeah. So,
I just want the mathematical statistics.
yeah,
That's all.
too much anthropomorphizing.
Well,
Fair enough.
I think there's a license to anthropomorphize a bit at this particular meeting.
It seems to me, for example, that like this machine learning stuff, like, man, these networks just want to learn. It does feel that way, but I know they don't want it. Maybe.
Give me a representation that explicitly says what want is. I'm just saying you're just doing inference in different dimensions.
Yeah.
Huge exponential pressure.
Yeah,
To do it in lower dimensions.
yeah.
I think that's the mathematical fact. I think over here we have, cognitive agents that want things. Great, let's model with wantings.
I
And
completely
you need that
agree.
in reinforcement learning.
Yeah, I completely agree with you.
Yeah.
You're describing what I'm trying to convey with the word want. Yes.
I mean, I think that there might just be a question of like, where does the pressure come from for the efficiency? And like, why
It's lower dimension.
why are we just not predicting more inefficiently? And I think that, yeah.
Resources, exponential different classes of resources.
Yeah. Yeah, if there's
Hugely.
finite resources,
Yeah.
and if there's
Right.
us and other agents competing in the world, if you can represent more efficiently, you'll have access to more of those resources.
I think the evolutionary story is definitely quite compelling. I think it's interesting in the ML case because we're giving them so much,
Yeah.
so many parameters. And yes, there's some tricks to have sparsify, etc. But I'm still a little bit surprised that they get so compressed.
Yeah, like even if you don't do weight decay and stuff, it just like
Right.
it goes to say I don't want to use any of my dimensions, and then it starts to use
Yeah.
them.
I think it's interesting.
Wait,
Yeah.
this happens even with no weight decay at all?
Yeah, this sort of stuff. It's really pretty wild.
That's very surprising to me. I have no idea where
Yeah.
the motivation to compress would come from.
The pressure.
The pressure, not the motivation.
Thank you. Appreciate that.
So I feel like we have been learning a lot by taking seriously that these representations are in a real vector space, doing experiments. The world has many parts, doing experiments. This certainly has implications for agents, and I think for us. I think we should be doing this stuff on brains also. So maybe the right team can make it happen. This seems like similar ideas ought to say something useful about what it's like for us to interact via this real vector space, and it's not going to be like the types of channels we talk about in information theory, I'd suggest. So I think there's a lot of work to do, and that's it for me.